Have you ever been there? You're absolutely redlining your high-speed CNC machine, trying to really push that material removal rate. The cut sounds perfect for maybe a second, and then, bam, this horrible, piercing, high-pitched squeal just rips through the shop.
Oh, yeah. That's the sound of money just evaporating. And then you stop the spindle, right? You look at the part, and there they are. Those awful, ugly chatter marks, ripples all over it when you wanted a mirror finish.
Exactly. You've just taken this incredible state-of-the-art machine and, well, basically turned it into an expensive way to wreck parts.
Temporarily, hopefully,
Uh,
but yeah, it's destructive.
That vibration, that chatter, it's like this silent thief working in the machine shop. It steals your accuracy for sure. It causes tools to just, catastrophically fail way too early. And it really beats up the expensive bits in your spindle.
It does. It puts immense stress on those bearings.
So today, we're doing a really critical deep dive. We're getting into how to control vibration, specifically in high-speed profile machining.
Hmm.
Our mission, really, is to figure out where this thief hides and give you a systematic, kind of four-pronged approach to kick it out.
And systematic is the key word there. This isn't just bad luck or random noise. Vibration is physics. It's predictable. So the main takeaway up front, to get stability, especially on those demanding profile jobs, you need a layered approach. You've got to optimize your cutting parameters. You need the shortest, stiffest tools you can possibly use. Your work holding needs to be rock solid. And then sometimes you need to bring in the smart stuff, the real-time damping technology.
A comprehensive defense. That's the only way to really unlock what these machines can do at high speeds.
Absolutely. It's the only way.
Okay, let's start unpacking that. Let's begin with diagnosis. When we hear that awful squeal, we know it's bad. But what's it fundamentally telling us? What's actually happening beyond just wrecking the surface finish?
It's telling you the system is actively destroying itself. Sometimes it's microscopic wear, accumulating over time. Sometimes it's rapid, visible damage. Yeah, poor surface quality, losing your dimensions. Those are the obvious things. But the hidden cost is huge. Chewing through expensive tools, wearing out spindle bearings way faster than you should. When you hear that squeal, you've hit what's called self-excited vibration.
Self-excited, meaning it feeds itself.
Exactly. The force of the tool cutting the material makes the tool shake. That shaking then increases the cutting force, which makes it shake more. It's a feedback loop that just amplifies itself until it's completely out of control.
Okay, so if we're trying to figure out why it's happening on a particular job, what are the main physical causes we should be looking for?
We can usually boil it down to four main areas.
Yeah.
First, and this is often the big one, is machine resonance. This happens when the frequency of the tool hitting the workpiece, basically, how many times per second the cutting edges strike matches a natural frequency, like an inherent wobble frequency of the tool itself or the holder or even the machine structure. Ah, like the swing analogy you mentioned earlier.
Precisely. Think about pushing a kid on a swing. If you just give it small pushes, but time them exactly with the swing's natural back and forth rhythm,
Yeah.
you can get that swing going incredibly high. Huge oscillation from small inputs. Same idea here, but it's destructive.
That makes total sense for the physics. But how does an operator, practically figure out that natural frequency for their specific setup? Because every tool and holder combo must be different, right? Can you measure that easily?
That's a great question because, yeah, every setup has its own signature. Engineers use software for this, running simulations, or sometimes they do what's called tap testing. Literally, you gently strike the tool with a special calibrated hammer, and you measure the vibration response with a sensor, like an accelerometer. That tells you the natural frequencies.
Okay, so you find the frequencies you need to avoid.
Exactly. Knowing those frequencies tells you which spindle speeds are likely to cause resonance, so you steer clear of them. It moves you away from just pure guesswork.
Right. What's the second cause? Second is simply uneven cutting force. If the force fluctuates wildly as the tool goes around, that can set up waves or ripples on the surface. Third is low system rigidity. Basically, something in the chain is flexing too much under load. Could be the machine frame, the tool holder, the fixture, even the workpiece itself. And finally, one that's easy to overlook, a worn or damaged tool. A dull tool doesn't shear the metal cleanly, it sort of plows through it. And that brings us to another important factor, something called stick-slip friction.
Stick slip, I've heard that term. It sounds like it's related to lubrication.
It is, but it's a bit more than just needing more coolant. Stick-slip happens when the cutting edge momentarily sticks to the material because of high static friction. Then, as the machine keeps pushing, the force builds up until it overcomes the friction and the tool suddenly slips forward. This cycle of stick but slip happens really fast, and it introduces these high-frequency jerky motions. It's a prime driver for chatter.
Especially with dull tools, or maybe the wrong speeds.
Exactly. Dull tools, running too slow in materials that like to work hard in.
Yeah, stick slip becomes a real problem, and poor lubrication makes it much worse, obviously.
Okay, so we've got the enemies identified. Resonance, shaky setups, dull tools, stick slip. Now let's talk solutions. How do we get past just randomly tweaking speeds and feeds, hoping for the best? We need a proper strategy.
We do. And like I said, engineers don't guess. They use data, often visualized in something called stability lobe diagrams. Picture a graph. On the vertical y-axis, you have the axial depth of cut, how deep you're going into the material. On the horizontal x-axis, you have the spindle speed in RPM. The diagram that gets generated looks like a landscape of hills and valleys, or lobes.
Okay.
The areas inside those lobes, those are the safe zones. Those are combinations of speed and depth of cut, where the cut will be stable and chatter-free. The areas outside the lobes, that's where the chatter monster lives.
So it's not just about going faster or slower. It shows there are specific stable speeds, and at those speeds, you might actually be able to cut much deeper. Precisely. That's the key insight. Stability isn't linear. You might find that a tiny change in RPM, maybe just 100 RPM up or down, can jump you from violent chatter right into a perfectly quiet, stable cut, or vice versa. And this directly informs the main strategy for a lot of successful high-speed profile work, which people often call the light and fast approach.
Okay, let's break that down. Light and fast. What does that actually look like at the machine?
It means you significantly reduce your depth of cut both radially, like side-to-side step over, and axially, how deep you plunge. You take a really small bite, maybe only 5 or 10% of the tool's diameter for the radial cut. But, and this is the key to keep your overall material removal rate, your MRR, high, you crank up the feed rate and the spindle speed. Way up. You're basically making up for the small bite size with sheer velocity.
Okay, and why is that better for stability? A shallow, super fast cut versus a deep, slow one.
Because you're keeping the cutting forces low and consistent. When you run at higher RPMs, you generally produce thinner chips. Thinner chips mean less force is exerted each time a cutting edge or flute engages the material. By taking a light cut but moving really fast, you distribute that cutting force over a longer path in the same amount of time. You avoid building up those big periodic forces that can excite the system's natural frequencies, especially the low-frequency ones. You trade depth for speed, get the same MRR, but you do it stably.
Got it. So parameters are dialed in using this light and fast idea, maybe guided by those stability lobes. Now, the tool itself, the thing actually doing the cutting, stiffness is king, everyone says that, but let's talk practicalities. Overhang, for instance.
Oh, the tool is huge. It's the first point of contact, and it's often the most flexible part of the whole setup. Think about tool overhang, how much sticks out from the holder. It's not a linear relationship with stiffness. If you double the length of that overhang, you don't just cut the stiffness in half, you reduce it by a factor of 8. It follows a cubic relationship.
Wow, 8 times less stiff just by doubling the length.
Yeah. That extra length acts like a massive lever. Any tiny force fluctuation at the cutting edge gets amplified hugely at the tip, turning into major vibration.
So the golden rule is always use the absolute shortest, stubbiest tool that can possibly do the job.
Always. No exceptions if you can help it.
But what about those times you have to use a long tool? You know, getting down into a deep pocket or machining an internal profile where there's no other way. That's where it gets tough.
That's where you need to get smarter with tool geometry and maybe specialized holders. You can fight back against that length penalty. First, look at the tool's geometry. Specifically, look for tools with a variable helix angle.
Variable helix, meaning the twist of the flutes isn't uniform.
Exactly. Or variable pitch, where the spacing between the flutes isn't even. The idea is that each cutting edge enters and exits the material at a slightly different time relative to the others. It breaks up the rhythm, it disrupts the steady harmonic beat that can build up into resonant chatter. You're essentially confusing the vibration.
Okay, clever. What else?
Second, for really long reaches, you might need to invest in specialized tool holders. Some have integrated damping features, maybe little sleeves or internal masses designed to absorb vibration energy. And of course, never ever skimp on the quality of the holder itself. It needs to be balanced impeccably for high OPMs. An unbalanced holder at high speed turns the whole tool assembly into this whipping, unstable mess before you even start cutting.
Right. Solid advice. So we've optimized the cut strategy, we've picked the stiffest possible tool, maybe one with smart geometry. But what if chatter still persists? The source material suggests we need to look beyond the tool and examine the whole foundation, right?
Correct. That brings us to segment 3, building that rock-solid foundation. Because if the tool is stiff, but the machine structure itself or the way you're holding the workpiece moves even a tiny bit under load,
Right.
well, then all that careful optimization upstream is pretty much wasted. Rigidity has to be end-to-end.
Okay. Obviously, starting with a heavy, solid machine base like cast iron helps a lot. But what about things that wear out over time?
Maintenance becomes critical. Even on the most massive machine, small amounts of wear can introduce enough play to cause big vibration problems. Things like worn spindle bearings, or loose gibs on the ways, maybe degraded linear guides. Any slop in the system is bad news under high cutting forces. So, checking and maintaining those components is non-negotiable before you even start chasing cutting parameters.
Makes sense. But you mentioned earlier the workpiece itself can be the source of low rigidity,
Yeah.
especially in profile machining, dealing with long, thin parts.
Precisely. That's often where the real battle lies, those long, slender profiles. They basically want to vibrate. They act just like guitar strings waiting to be plucked by the cutting tool. They have very low natural frequencies, which means they're easily excited into vibrating, often quite violently, so just clamping them down at the two ends and hoping for the best. Usually that's a recipe for Chatter City. The work holding setup needs to be as rigid as the machine table itself.
So the solution isn't just more clamping force, but maybe where you clamp.
It's absolutely strategic clamping. The key insight here is using multiple clamping points distributed along the length of the profile. You're not necessarily clamping it harder overall, but you are dramatically shortening the unsupported length of the material between clamps. By breaking the long guitar string into multiple shorter, stiffer segments, you effectively raise its natural frequency.
So you push its vibration tendency up into a higher frequency range that the cutting process is less likely to excite.
Exactly. You make each section too short and stiff to easily resonate at the cutting frequencies. And for parts that are really delicate, maybe thin-walled, or have complex shapes where clamps would distort them, that's where you look at more advanced solutions. Things like vacuum chucks or high-power magnetic tables. These provide continuous, uniform support across a large area of the part surface.
Instead of just discrete points.
Right, and that continuous contact does a great job of damping vibration, too. It absorbs the kinetic energy over the whole surface.
Okay, so we've got finesse with parameters, physics with tool selection and stiffness, and structural integrity through solid fixturing and smart clamping. But what about those truly tough jobs, the really demanding materials or extreme geometries where even all that optimization just isn't quite enough? We need an even smarter edge.
That's where we get into the really interesting stuff. Dynamic compensation and real-time monitoring. We shift from setting things up statically and hoping for the best to having the system actively sense and adjust itself in milliseconds. We stop predicting and start reacting.
So how does the machine literally listen to the cut to know if chatter is starting?
It uses highly sensitive industrial sensors, mostly accelerometers, but sometimes acoustic emission sensors too. These are mounted strategically, often right on the spindle housing or very close to it. They act like the machine's ears. They are constantly monitoring the vibration signature, tiny changes in amplitude and frequency that are the telltale signs of oncoming chatter, often long before a human could hear it or see its effects. This sensor data provides a live feed straight to the machine's control system.
And the control system is the brain that uses this live feed. How fast can it possibly react?
Almost instantaneously. This is what we call adaptive control. It's a closed-loop system. The sensors pick up a vibration pattern that indicates chatter is about to start. The control system compares this data to its internal stability map. Remember those lobe diagrams. And if it sees the process drifting towards an unstable zone, the adaptive control automatically tweaks the cutting parameters. Usually it adjusts the spindle speed, sometimes the feed rate. It does this in milliseconds to nudge the process back into a known stable cutting zone. It's like continuous, automatic course correction.
That's seriously impressive. But the sources mention something even more advanced. Active damping. That sounds almost like science fiction fighting vibration with vibration.
It is the ultimate countermeasure, and yeah, it's a real game changer, especially for those long-reach tools or really high-performance operations. Active damping systems typically use special actuators. Often, these are piezoelectric actuators, materials that change shape very rapidly when voltage is applied. These actuators are built right into the tool holder or sometimes even integrated into the spindle itself.
Okay, so how does an actuator cancel vibration?
It generates an equal and opposite force. When the sensors detect the tool starting to vibrate in one direction, say moving upwards, the control system instantly calculates the necessary counterforce and tells the piezoelectric actuator to push downwards with precisely the right timing and magnitude. If the tool moves left, the actuator pushes right. It creates a counter vibration that is exactly 180 degrees out of phase with the chatter vibration.
So they literally cancel each other out.
If the actuator has enough power and speed, yes, it effectively neutralizes the chatter wave before it can grow. Think of it like noise-canceling headphones, but for physical motion at the tooltip.
Wow. That's the difference between just trying to stay within the stable zones
Yeah.
and actually expanding those stable zones by actively killing the vibration. That must unlock cutting performance that would be completely impossible otherwise.
It absolutely does. It directly compensates for the inherent flexibility in the tool, the workpiece, the machine.
Right.
It pushes the stability limits way out.
Okay, so let's bring this all together. We've gone from the basics of hearing that squeal all the way to fighting chatter with piezo actuators. What it tells us is that achieving that smooth, quiet, high-speed cut isn't about one magic bullet. It's this comprehensive, multi-layered strategy. You need the finesse in your parameters, the physics right in your tool choice and stiffness, the rock-solid foundation in your fixturing, and then we're needed leveraging this really intelligent adaptive tech. Mastering all that is how you take a powerful machine and make it truly precise, truly high-speed, and ultimately profitable.
Couldn't agree more. Vibration isn't some random gremlin that shows up. It's a predictable outcome of the entire system's dynamics. It has clear causes, resonance match, lack of stiffness, friction issues, and these causes can be systematically addressed and eliminated. At the end of the day, true high-speed quality is completely dependent on achieving and maintaining system stability.
A perfect summary. And for you listening right now, we want to leave you with a final thought to maybe noodle on. We talked a lot about how critical minimizing tool overhang is and how vital multi-point clamping is for supporting long, thin parts. But what if you encounter a situation with an ultra-long, maybe extremely delicate profile, where traditional clamping just isn't feasible? Maybe it would crush the part, or the shape makes it impossible. What kind of non-traditional fixture material or perhaps even fixture geometry could you research or design? Something that might provide passive damping, absorbing vibration energy, even without applying heavy clamping force. Think about materials or structures that naturally dissipate energy, providing that rock-solid vibration-killing foundation in a completely different way.
Something to think about. Happy machining!